Reality might be a tiny sliver of the whole picture. We are about to go on a thrilling journey into the cosmos's greatest enigma, the hidden dimensions of existence. This is a deep dive into 30 mind-blowing theories that will permanently challenge your perception of the universe. You will gain a new framework for understanding everything, from the tiniest vibrating strings to the vast, unseen architecture of all space. How can extra dimensions be curled up smaller than an atom? And what colossal structures could be floating right next to us, completely invisible? The answers reshape what it means to exist. What feels most real to you about the world you see? The very fabric of our universe might be woven from music. This is the stunning proposal of superstring theory, the first of our 30 great ideas. It says that if you could peer down into the heart of an electron or a quark, you would not find a tiny, solid dot. Instead, you would discover a shimmering, vibrating loop of energy, a string. And just like the strings on a violin, how they vibrate determines the note they play. In this cosmic symphony, the different vibrational patterns of these fundamental strings create all the particles we see, the quarks, the photons, everything. The electron is one note, the photon is another. It is a beautiful, unified idea, but it comes with a profound catch. The mathematics of these vibrating strings only works, it only stays in tune, if the universe has more room to breathe than we can perceive. Specifically, it demands 10 dimensions. We experience 3 of space, length, width, and height, plus the single flow of time. That leaves 6 spatial dimensions completely unaccounted for, hiding from our senses. So where are they? Think of a long garden hose stretched across a field. From a distance, it looks like a simple one-dimensional line, but an ant crawling on its surface knows the truth. It can move along the hose's length, but also in a tight, circular path around its tube. That second dimension is curled up or compactified, so small that from our human-scale viewpoint it disappears. Superstring theory suggests our entire reality is like that. Those 6 extra dimensions of space are curled up into an unbelievably tiny, complex shape at a scale called the Planck length, which is a millionth of a billionth of a billionth of a billionth of a centimeter. They are woven into the fabric of every single point in our familiar 3-dimensional space, like a hidden, intricate pattern too fine for any instrument to detect. This means that at every location you can point to, in the air around you, within your own hand, there exists a whole hidden geometric world, a 6-dimensional labyrinth of unimaginable smallness, dictating the laws of physics through its shape. The vibrations of the strings are confined by this shape, which is why we get the specific particles and forces we do. It is a breathtaking vision, one where the universe's deepest rules are set by the geometry of unseen, compactified dimensions. But if 6 dimensions can hide, what about even more? Superstring theory's elegant symphony of 10 dimensions was not the final movement. Physicists soon realized there were not 1, but 5 distinct versions of string theory, each mathematically valid but telling a slightly different story about the cosmos. It was a puzzle, a cosmic cacophony where everyone was playing a beautiful tune, but they were not quite in harmony. Then came a revelation so profound it reshaped the entire field, a master theory that wove these 5 separate ideas into one grand, unified tapestry. This is M-theory, and its first stunning declaration is that our universe has one more dimension than we thought. Not 10, but 11. That 11th dimension is not like the others. While the 6 extra dimensions of string theory are curled up incredibly small, this new dimension might be vast. It is the stage, the higher dimensional arena in which everything else exists. Think of it as a boundless, impossible-to-picture expanse called the bulk. Within this 11-dimensional bulk, the fundamental objects are not just one-dimensional strings. M-theory introduces membranes, or branes for short. These can have many dimensions. A 2-dimensional brane is like a sheet, a three-dimensional brane is a volume, and they can exist all the way up to 9 dimensions. Our entire universe, with all its galaxies, stars, and planets, could be one such membrane, specifically a three-dimensional brane, often called a three-brane, floating within this vast bulk. Everything we know, every particle of matter, every force except gravity, might be stuck to the surface of this brane like ink on a page. We cannot leave it. This explains why we only perceive 3 spatial dimensions, because our reality is literally painted onto a three-dimensional canvas adrift in a higher dimensional sea. But what about gravity? In this breathtaking framework, gravity is the lone wanderer. It is the only force that can leak off our brane and seep out into the bulk. This could explain why gravity is so astonishingly weak compared to the other fundamental forces. A magnet can easily pick up a paperclip, defeating the gravitational pull of the entire Earth because gravity's strength is diluted as it spreads out into the hidden dimensions. This single idea of our universe as an island floating in a higher dimensional ocean opens the door to possibilities that are nothing short of revolutionary. If there are other branes out there in the bulk floating parallel to our own, what might exist on them? The geometry of those hidden 6 dimensions is not random. It has a name and a breathtakingly beautiful form, the Calabi-Yau manifold. This is the specific, intricate shape where the extra dimensions of string theory are curled up, and its structure dictates absolutely everything about our visible universe. Think of it as the cosmic DNA of reality, a 6-dimensional geometric code written into the fabric of every point in space. The properties of this shape, its specific twists, holes, and folds, directly determine which vibrational notes the fundamental strings can play. In essence, the Calabi-Yau manifold is the instrument, and the strings are the musicians. The shape of the instrument decides what music can be made. One particular fold in the manifold might correspond to the vibrational pattern that creates an electron, while a different, more complex loop might produce a quark. Even the forces of nature, like electromagnetism and the strong nuclear force, emerge from the specific topology of this hidden geometry. The number of holes and tunnels in a Calabi-Yau manifold, features mathematicians call handles, has a direct and profound consequence. It influences how many generations of fundamental particles the universe contains. We observe 3 generations of matter, the up quark and down quark, the charm and strange quark, the top and bottom quark, and their corresponding leptons like the electron, muon, and tau. Why 3? The answer may be written in the 6-dimensional labyrinth of the Calabi-Yau shape, in the count of its topological features. Visualizing these shapes is a challenge for our 3-dimensional minds. They are not solid objects but complex, multi-dimensional surfaces, often described as looking like intricate, multi-hole donuts or fantastically sculpted glass woven through with tunnels and lobes. If you could somehow shrink down to the Planck scale and peer into the heart of space, this is what you might see at every location, a shimmering, constantly vibrating sculpture of pure geometry, more beautiful and complex than any cathedral. The specific Calabi-Yau shape that corresponds to our universe would explain why the constants of nature, like the strength of gravity or the mass of an electron, have the precise values they do. Find the right shape and you find the blueprint for everything, but this leads to a staggering and slightly unsettling possibility. Mathematics suggests there is not just one possible Calabi-Yau manifold. There are perhaps 10 to the 500 different versions. That is a 1 followed by 500 zeros, a number so vast it dwarfs the count of atoms in the observable universe. Each one is a valid solution, a possible 6-dimensional shape for the hidden dimensions, and each one would produce a universe with completely different physics. If the shape is different, the vibrational notes are different, meaning different particles, different forces, and laws of nature we would not recognize. This raises a question of cosmic proportions. Did our particular Calabi-Yau manifold, the one that gives us electrons, stars, and life, get chosen by some profound law, or is it just one possibility among an almost infinite landscape of others? This dizzying landscape of possibilities forces us to ask a more fundamental question. What is reality truly, and where does information actually reside? The answer may be the most disorienting idea in all of physics. Our three-dimensional universe, with all its rich depth and volume, could be a magnificent illusion, a hologram. This is not a metaphor for something vague. It is a precise mathematical principle born from the most extreme objects we know, black holes. When matter falls into a black hole, it vanishes from our universe, seemingly erasing all information about what it was, which violates a core tenet of quantum mechanics. In the 1970s, physicist Jacob Bekenstein made a startling calculation. He found that the maximum amount of information, the total entropy, a black hole can contain is not proportional to its volume as you might expect. It is proportional to the surface area of its event horizon. Think about that for a moment. All the data describing everything that ever fell into the black hole is not stored within its vast interior volume. It is encoded on its two-dimensional boundary, like a cosmic hard drive with pixels the size of a Planck area. This bizarre fact led physicists Gerard T. Hooft and Leonard Susskind to propose a principle so radical it reshapes our concept of existence. The holographic principle states that all the information contained within any volume of space can be fully described by physics operating on the lower dimensional boundary of that region. Our universe, with its three spatial dimensions, might be a holographic projection from a two-dimensional surface at the cosmic edge. To grasp this, picture a common security hologram on a credit card. The flat, shiny sticker holds no three-dimensional image you can see, but when light hits it at the right angle, a fully three-dimensional eagle or globe seems to pop out with genuine depth and parallax. All the data needed to create that three-dimensional illusion is compressed onto the two-dimensional surface of the sticker. The holographic principle suggests our reality works the same way on a cosmic scale. Every star, every planet, every person, every event happening in the three-dimensional volume of the cosmos could be a projection. The true, fundamental description of the universe, the code of reality, is written on a distant, two-dimensional shell that surrounds everything. In this view, we are not solid beings moving through a solid world. We are complex, dynamic interference patterns like ripples on the surface of a pond, but the pond is the edge of the universe and the ripples are everything we experience. The depth we feel, the space between objects, is an emergent property, a grand illusion generated by information processing on that lower dimensional screen. This means the universe has a fundamental pixelation, a limit to how much detail any region can contain, set by its surface area, not its volume. It is a breathtaking trade-off where the richness of our three-dimensional experience is purchased at the cost of living inside a projection. If this is true, then the quest to understand the hidden dimensions takes a profound turn. We are not just missing curled-up dimensions, we might be living inside one giant, projected consequence of a simpler, flatter, truer reality. But a holographic projection from where? The search for that fundamental screen leads us to a theory where universes are born not from a single point but from a shattering impact. This is the ekpyrotic model, and it rewrites the very first moment of everything. Forget a hot, dense singularity. In this brane cosmology, our universe begins with a cold, quiet, and nearly empty three-dimensional brane floating parallel to another in the higher dimensional bulk. These two branes are like immense cosmic sheets separated by a tiny gap. Over eons, they are drawn together by the gentle pull of gravity leaking through the bulk. They move slowly at first, then faster until they finally collide. That collision is our Big Bang. It is not an explosion from a point, but a universe-wide event where kinetic energy from the impact is converted into the searing heat and dense matter that filled the early cosmos. The violence of the collision creates ripples across the surface of our brane, which eventually become the seeds for galaxies. This model elegantly sidesteps the need for a singularity, a point of infinite density where our laws of physics break down. Instead, the beginning is a well-defined physical event, a clash of titanic membranes in a hidden dimension. But what happens after the collision? Do the branes stick together and stop? Perhaps not. They might simply bounce off each other like two enormous sheets of rubber and drift apart in the bulk. As they separate, our universe expands and cools exactly as we observe. But the story does not end there. This leads to the even more profound cyclic model. Imagine those two branes now drifting apart after their fiery creation of our cosmos. The gravitational attraction between them never stops. Eventually, their outward motion slows, halts, and reverses. Over trillions of years, they are pulled together once more for another cataclysmic collision, sparking a brand new Big Bang and a whole new universe on the surface of the brane. In this breathtaking vision, the cosmos is not a one-time event with a definite beginning and end. It is an eternal, rhythmic cycle of creation, expansion, contraction, and rebirth. Each cycle erases the large-scale structure of the old universe, but may imprint subtle clues from one incarnation to the next. This model also provides a compelling alternative to cosmic inflation, the theory of a super-fast expansion right after the Big Bang. In the cyclic picture, the smooth, uniform universe we see is not the result of a brief inflationary sprint, but a consequence of the branes being stretched and smoothed flat during the long, slow phases between collisions. Our entire cosmic history, from the first light to the last star, becomes just one chapter in an endless, repeating saga of colliding worlds. We are living in the aftermath of one such impact on the surface of a still reverberating membrane, awaiting the next inevitable convergence in the silent, higher dimensional dark. Yet this eternal cycle of cosmic collisions raises a profound question about the nature of choice itself. What if every single decision, every quantum flicker of possibility, does not just fade away, but instead creates an entirely new cosmos? This brings us to a theory that redefines the concept of hidden dimensions, not as curled-up spaces or distant branes, but as entire parallel worlds unfolding right alongside our own. This is the many worlds interpretation of quantum mechanics, and it begins with a simple, almost unsettling premise. In the strange realm of the quantum, particles exist in a haze of probability called a superposition. An electron is not here or there, it is both, a cloud of potential locations until we look at it. The act of observation, of measurement, seems to force it to pick a single, definite state. This is the famous measurement problem, but physicist Hugh Everett asked a radical question in the 1950s. What if the measurement is not forcing a choice, but is instead a branching point? What if, when the electron's position is measured, the universe itself splits? In one new, freshly spawned reality, the electron is found here. In another, completely separate but equally real reality, it is found there. Both outcomes happen, but they become disconnected from each other, forever diverging. This is not a metaphor. In the many worlds view, every quantum event with multiple possible outcomes causes the entire cosmos to bifurcate, creating new, parallel universes that contain every single possible version of that event. These are not dimensions of space you could travel through with a ship, but they are additional, full-fledged dimensions of reality, entire timelines that coexist alongside ours in an ever-expanding, infinite-dimensional structure physicists call the quantum multiverse. To understand the staggering scale, consider the classic thought experiment of Schrödinger's cat. A cat is placed in a box with a device that will release poison based on the random decay of a single radioactive atom. According to standard quantum mechanics, until you open the box, the atom is in a superposition of decayed and not decayed, and therefore the cat is in a superposition of both alive and dead, a paradoxical state. The many worlds interpretation resolves this neatly and without paradox. When you open the box, you do not find a ghostly half-dead cat. Instead, the universe splits. In one branch, you open the box and find a living cat, and the you in that universe always saw the atom not decay. In the other, completely separate branch, you open the box and find a deceased cat, and that version of you always observed the atom decay. Both yous are equally real, both experiences are genuine, but they are now forever isolated, unaware of each other. Now, extend this from a single atom to every particle in the cosmos. Every quantum fluctuation in every star, every random event in every brane, every possible choice you could have made but did not, is realized somewhere in this vast, branching tree of realities. In one dimension of existence, you took that different job. In another, a different outcome to a historical election changed the world. In yet another, the laws of physics themselves are subtly different because some early quantum fluctuation went another way. The philosophical implications are immense. It suggests a cosmos of truly infinite variety, where every tragedy is balanced by a triumph in another branch, and every missed opportunity is fully lived out in a parallel world. It removes any special role for consciousness in collapsing quantum states. The universe just keeps branching mechanically, and it presents a hidden architecture of existence far vaster than any curled-up dimension, a fractal tapestry of all possible outcomes, with our lived experience being just one thread in an unimaginably complex weave. But if every possibility exists somewhere, what does that say about the uniqueness of our own path? And could there be a way, however faint, to catch a glimpse of those other branches? The branching multiverse offers a dizzying view of hidden realities, but it leaves one fundamental force feeling strangely out of place. Why is gravity so unimaginably feeble? A tiny magnet can lift a paperclip, defeating the gravitational pull of an entire planet. This is the hierarchy problem, a glaring imbalance in the strength of nature's forces, and the answer may lie in the very architecture of higher dimensional space. To find it, we must return to the concept of the bulk, the vast, unseen arena proposed by M-theory. Think of the bulk as an infinite, higher dimensional ocean. Our universe is not floating freely in it, but is more like a slice, a three-dimensional island or membrane called a brane, suspended within this immense depth. This is the core of brane world scenarios. In this picture, most of the particles and forces we know, like electrons and photons and the nuclear forces, are fundamentally stuck to our brane. They are like waves that can only travel along the surface of the ocean, unable to escape into the depths. But gravity is different. Gravity, in the form of the fabric of spacetime itself, can leak off our brane and seep out into the surrounding bulk. This single idea, developed in models like those by physicists Lisa Randall and Raman Sundram, provides an elegant solution to the mystery of gravity's weakness. Imagine you have a drop of powerful ink. If you place it on a small, absorbent paper towel, it creates a dense, dark stain. But if you drop that same ink into a vast swimming pool, it diffuses, spreading out and becoming incredibly diluted. Gravity is that ink. In our familiar three-dimensional world, we only experience the tiny, diluted fraction of gravity's true strength that remains stuck to our brane. The vast majority of its influence has bled away into the extra dimensions of the bulk. This is why the force that holds galaxies together feels so weak at our human scale. It is literally leaking into a hidden realm. The Randall-Sundram models propose a specific, warped geometry for this bulk. It is not a flat, featureless ocean, but a space that is intensely curved like a steep valley with our brane sitting at one edge. This warping acts to localize gravity very close to our brane, so it still behaves according to Newton's and Einstein's laws over astronomical distances, but its fundamental strength is diluted because the bulk is there, just a microscopic step away in a direction we cannot point to. Visualize it this way: picture our three-dimensional universe as the two-dimensional surface of a pond. The ripples from a pebble, representing forces like light, travel only along that surface. But gravity is like a sound wave from that same pebble hitting the water. It propagates in all directions, including up into the air and down into the depths. We on the surface only feel a faint echo of the full vibration. This elegant leakage not only explains gravity's feebleness, but also opens a door to a terrifying and magnificent possibility. If our brane is just one island in the bulk, what else might be floating out there in the dark? Long before strings or branes, a quiet revolution began with a single, elegant letter. In 1919, just as Einstein's theory of gravity was reshaping physics, a relatively unknown mathematician named Theodore Kaluza sent a paper to Einstein himself. Kaluza had performed a breathtaking act of mathematical daring. He took Einstein's equations for general relativity, which described the warping of four-dimensional spacetime, and simply rewrote them for a universe with one more dimension, a fifth. The result was astonishing. The familiar equations for gravity were still there, perfectly intact, but something new emerged from the extra terms, a set of equations that looked exactly like James Clerk Maxwell's famous laws of electromagnetism. In one stroke, Kaluza seemed to have unified the two great forces of his day, gravity and light, by proposing that our universe has a hidden fifth dimension. Einstein was initially stunned, then deeply intrigued. He held onto the paper for 2 years, pondering its implications before finally helping to get it published. The idea was brilliant, but it faced an obvious and crushing question. Where is this fifth dimension? We do not see it. The answer came a few years later from Swedish physicist Oskar Klein. He proposed that this extra dimension is not large and expansive like the three we know. Instead, it is curled up into an unbelievably tiny circle, a loop with a radius perhaps as small as the Planck length. Imagine a long, thin garden hose stretched across a field. From a distance, it looks like a simple one-dimensional line, but an ant on the hose knows it can also move in a tiny circle around the hose's circumference. That circular path is the hidden dimension, present at every point along the hose's length, but so small it is invisible from afar. Klein suggested our reality is exactly like that. At every single point in our familiar three-dimensional space, there exists this minuscule, circular fifth dimension. We are like the ant, but we are so large compared to the loop that we are completely unaware of its existence. Our entire world is stuck on what is called the zero mode, the simplest, most uniform vibration around that tiny circle. But the magic happens when we consider how a particle might move in this hidden geometry. Think of a single point representing a fundamental particle like an electron existing in this five-dimensional world. It can move through our three large dimensions, which we see as its position in space. But it can also have momentum, a kind of swirling motion around that tiny, compactified fifth circle. From our limited, four-dimensional perspective, we cannot perceive the particle zipping around the microscopic loop. What we detect instead is a conserved quantity, a property that does not change. That property is electric charge. In the Kaluza-Klein theory, the electric charge of a particle is not some arbitrary tag attached to it. It is a direct consequence of the particle's momentum in the hidden fifth dimension. An electron has a certain specific momentum around that tiny circle, which we measure as a negative charge. A positron, its antimatter counterpart, would have momentum in the opposite direction, giving it a positive charge. A photon, a particle of light, would have no net momentum around the circle and thus carries no electric charge. The geometry itself gives birth to the force. The curvature and vibrations in this five-dimensional spacetime produced both the warping we feel as gravity and the electromagnetic fields that power our world. It was a vision of stunning unity, where the forces of nature were not separate entities but different facets of a single, higher dimensional geometry. While the theory ultimately could not account for the other nuclear forces discovered later, its legacy is monumental. It was the very first unified field theory, a direct inspiration decades later for the architects of string theory. Kaluza and Klein showed that hidden dimensions were not just science fiction, but a powerful mathematical tool that could reveal a deeper, more connected cosmos. They planted the seed for everything that followed, a quiet proof that sometimes the answers are not in front of us, but curled up in a direction we never thought to look. The staggering number of possible Calabi-Yau shapes leads us directly to one of the most profound and controversial ideas in modern physics: the string theory landscape. This is not a physical place you could ever visit, but a mathematical terrain of almost unimaginable scope. Each valid Calabi-Yau manifold, each distinct way of curling up those 6 hidden dimensions, represents a different possible vacuum state, a unique set of ground rules for a universe. The mathematics suggests there could be 10 to the power of 500 such possibilities. That number is so vast it has no name, a 1 followed by 500 zeros. It dwarfs the number of atoms in our entire observable cosmos. Each point in this abstract landscape corresponds to a fully realized universe with its own unique laws of physics, its own particles, its own fundamental constants. In one universe, the strength of gravity might be 1,000 times stronger, making stars burn out in a cosmic blink. In another, the nuclear forces might be too weak to ever form atoms. Most of these universes would be sterile, empty, or chaotic voids, utterly incapable of supporting any form of complexity, let alone life. This raises an unavoidable and deeply philosophical question. Why does our universe have the precise, finely tuned set of laws that allow for galaxies, planets, and conscious beings like us to exist? The landscape offers a startling answer known as the anthropic principle. It suggests there is no deeper reason why our particular set of laws was chosen. We do not live in a special or uniquely designed cosmos. Instead, we simply find ourselves in one of the rare, habitable corners of an infinite cosmic garden. In this vast multiverse of possibilities, every possible set of physical laws is realized somewhere. We could not possibly observe a universe incompatible with our own existence. We are here because this bubble, with its specific Calabi-Yau shape giving us electrons, stable atoms, and long-lived stars, allows observers to arise. It is a cosmic version of the observation that a fish does not wonder why it lives in water. It simply could not live anywhere else. The landscape transforms our search for a single, elegant theory of everything into a statistical endeavor. The fundamental question may not be why these laws, but rather, what is the mechanism that allows different bubbles in this landscape to become real, breathing universes? This shifts our gaze from the geometry of hidden dimensions to the very fabric of spacetime itself, and to a process of cosmic reproduction more prolific than anything we have yet conceived. The dream of a single equation that describes everything is the ultimate goal of physics. It is called the theory of everything, a framework so complete it would weave together the 4 fundamental forces and all the particles of nature into one seamless tapestry. For centuries, these forces have been described by separate rule books. Gravity, governing the cosmos, is explained by Einstein's general relativity, a theory of the smooth curvature of spacetime. The other 3 forces, electromagnetism, the strong nuclear force that binds atomic nuclei, and the weak nuclear force behind radioactivity, are described by quantum field theory, a realm of probability and discrete particles. The problem is these 2 rule books are written in incompatible languages. General relativity paints a continuous, geometric picture of reality, while quantum mechanics insists on a grainy, probabilistic one. When pushed to extremes like the center of a black hole or the first instant of the Big Bang, the 2 theories clash violently and our understanding of reality breaks down. This is where hidden dimensions offer a breathtaking path to unity. They are not merely mathematical curiosities, but the potential master key that could unlock a single, coherent description of the cosmos. Think of our current situation like trying to understand a magnificent, three-dimensional sculpture by only examining its two-dimensional shadows cast on a wall. From one angle, you see a circle, from another, a square, from a third, a complex star shape. Each shadow is real and accurate from its own perspective, but they seem contradictory. They are all incomplete glimpses of a higher dimensional object you cannot directly see. In our quest for a theory of everything, gravity and quantum mechanics are those conflicting shadows. Hidden dimensions propose that both are projections of a single, richer reality that exists in more than the four dimensions we experience. By adding these extra dimensions to our equations, we are not complicating the universe, we are simplifying it. We are stepping back to see the full sculpture. In the framework of string theory and M-theory, the vibrations of strings in a 10 or 11-dimensional arena produce all the particles and forces as different modes of the same fundamental object. The graviton, the hypothetical particle carrying gravity, emerges as one specific vibrational pattern. The photon, carrier of electromagnetism, emerges as another. The particles of the strong and weak forces emerge as yet others. In this higher dimensional space, the forces are not separate at all. They are different notes played on the same cosmic instrument. The dream is that the single, elegant equation we seek would not describe our four-dimensional world directly, but would define the geometry and dynamics of that higher dimensional arena. Our familiar laws of physics, with all their apparent complexity and separation, would then naturally flow out of that equation like different facets of a gem emerging from a single, perfect cut. The hidden dimensions are the stage upon which this ultimate unification play can be performed. Without them, the actors have no room to perform their roles in harmony. Finding the right mathematical shape for those dimensions, the correct Calabi-Yau manifold or brane configuration, is the search for the specific stage design that produces the exact universe we observe. It is a quest to read the architect's original blueprint, written in a language of geometry we are only beginning to decipher. The search for that single unifying equation often leads us to look for its fingerprints in the cosmos, relics from the universe's violent birth. Among the most exotic predictions are cosmic strings, not to be confused with the fundamental strings of string theory. These are gargantuan, one-dimensional defects in the fabric of spacetime itself. Picture the early universe cooling from an unimaginably hot, symmetric state, much like water freezing into ice. As water freezes, the crystalline structure doesn't form perfectly uniformly. Defects form lines where the ice crystals misalign. Cosmic strings are thought to be similar, but on a cosmic scale. They are ultra-thin, perhaps no wider than a proton, yet they could stretch across the entire observable universe. Their density is staggering. A single inch of a cosmic string might weigh as much as a mountain range. They are not made of matter as we know it, but are pure wrinkles in the geometry of spacetime. Regions where space is so severely pinched that it forms a true one-dimensional line. In our standard four-dimensional universe, these strings would generate intense gravitational fields, and if they moved, create ripples in spacetime called gravitational waves. But when we introduce the concept of hidden, compactified dimensions, the story of cosmic strings becomes even stranger and more revealing. In a universe with extra curled-up dimensions, these colossal strings could exhibit a fascinating property. They might not just exist in our three large dimensions. A cosmic string could also wrap around one of those tiny, hidden circular dimensions, like a thread winding around a microscopic spool. This wrapping has profound consequences. From our macroscopic perspective, we wouldn't see the string winding through that invisible, compact direction. Instead, that wrapped configuration would impart unique properties to the string we can observe. It could affect how the string interacts with other objects, how it moves, and most intriguingly, the specific pattern of gravitational waves it would emit. A wrapped cosmic string would be a direct fossil, a cosmic artifact encoding information about the size and shape of the hidden dimensions it is entangled with. Its vibrations would not just be in our familiar space, but would also involve oscillations in that compactified loop. Searching for the gravitational wave signatures of cosmic strings is therefore a hunt for two mysteries at once. Detecting one would confirm the existence of these primordial spacetime defects, but analyzing its signal could, in principle, reveal the hidden notes of higher dimensional geometry. It would be like listening to a bell ringing and being able to deduce not just the bell's material, but the exact shape of the hidden chamber it is ringing inside. While no definitive cosmic string has been found, their potential discovery offers a thrilling possibility. We might not need a particle accelerator the size of a galaxy to probe the Planck scale. The universe itself may have left us enormous vibrating clues, threads woven through the very fabric of reality that, if we learn to read their hum, could whisper the secrets of dimensions we cannot see. Gravity's puzzling weakness finds a stunning geometric solution in the warped landscapes of extra dimensions. The Randall-Sundrum model, a brilliant refinement of brane world ideas, proposes that the hidden dimension is not just large but profoundly curved. This curvature is not a gentle bend, it is an extreme warping described mathematically as an anti-de Sitter space. Picture this not as a flat, featureless corridor, but as a steep, plunging valley. Our universe, our three-dimensional brane, sits at one edge of this valley at the steep cliff face. Another brane, often called the Planck brane because it sets the fundamental scale of gravity, sits at the opposite, far edge of this warped gorge. Now consider gravity itself, embodied by the hypothetical graviton particle. In this model, gravitons are not confined to our brane, they can propagate through the entire warped bulk. But the steep curvature of the space acts like a powerful filter or a diluting agent. The intensity of the gravitational force falls off exponentially as it travels from the distant Planck brane across the warped dimension to reach our brane. It is as if gravity's signal must climb out of a deep, energy-sapping well to get to us. By the time it arrives at our location in the higher dimensional geography, its strength is only a faint echo of its original power. This exponential suppression is the key. It means that even if the extra dimension is only moderately large in terms of its true warped distance, the effect on gravity's strength is colossal. We perceive gravity as incredibly weak because we are living in a cosmic location where its influence has been drastically diluted by the warped geometry of the hidden dimension itself. A powerful analogy is to think of a lighthouse beacon shining across a foggy, turbulent sea. The light originates with brilliant intensity at the source, the Planck brane lighthouse. But as it travels through the thick, warped medium of the foggy bulk, its light is scattered and absorbed. By the time it reaches our ship, our brane, we only see a dim, diffuse glow. All the other forces, like electromagnetism, are like signals traveling along the rigging of our own ship. They do not have to brave the foggy bulk, so they remain strong and undiluted. This elegant warping does more than just explain gravity's feebleness. It also naturally solves the hierarchy problem, that vast gap between the strength of gravity and the other forces, without requiring any artificial fine-tuning. The geometry itself does the work. It suggests that the constants of nature we measure are not fundamental, but are local environmental effects determined by our specific address in a warped, higher dimensional cosmos. If we could somehow slide our brane closer to the gravity source in the bulk, the force would grow stronger, fundamentally altering the nature of our reality. This warped dimension is not a passive hiding place, it is an active sculptor of physical law, its curvature written into the very strength of the pull that holds our feet to the ground. This profound warping of gravity leads us to a mystery even more fundamental than the strength of a force, a riddle about the very emptiness of space. The cosmological constant problem is perhaps the most shocking mismatch between theory and observation in all of science. When we try to calculate the energy of the vacuum, the empty space between stars and atoms, using our best theories of quantum mechanics, we get a number. And that number is catastrophically wrong. It predicts that empty space should possess a staggering density of energy, a repulsive force so powerful that it would have ripped the universe apart in the first fraction of a second of its existence, preventing any galaxy, star, or planet from ever forming. Yet when we look out at the cosmos, we measure the actual energy of the vacuum, what we call dark energy. It is there, causing the expansion of the universe to accelerate, but its value is almost zero. Not just small, but 120 orders of magnitude smaller than the theoretical prediction. That is a 1 divided by a number with 120 zeros after it. It is the most precise and baffling fine-tuning ever conceived. Why is the energy of nothingness so close to zero, yet not exactly zero, and just the right minuscule value to allow our universe to unfold? Hidden dimensions and the vast landscape of string theory offer a startling, if humbling, explanation. In the landscape of 10 to the 500 possible universes, each with its own Calabi-Yau shape and physical laws, the value of the cosmological constant is just another dial that can be set to almost any number, positive, negative, or zero. The vast, overwhelming majority of these settings produce universes that are either stillborn or instantly torn apart. A large positive constant blows everything apart before structure can form. A large negative constant causes a catastrophic, rapid collapse. Only in an incredibly narrow sliver of this cosmic parameter space, where the vacuum energy is almost perfectly balanced at a value very near zero, do you get a universe that expands gently enough for gravity to pull matter together over billions of years, forming galaxies, stars, and planetary systems where life could potentially arise. This is the anthropic principle applied with brutal logic. We do not observe a universe with a large cosmological constant because such universes have no observers. They are empty, chaotic, or fleeting. We find ourselves in a universe with an impossibly tiny amount of dark energy for the same reason a fish finds itself in water. It is the only environment in which its form of existence is possible. In this view, the cosmological constant is not a fundamental constant dictated by a beautiful, unique equation. It is an environmental accident, a local address in the landscape. Our bubble universe just happened to nucleate with this specific, life-permitting value. The staggering fine-tuning is not evidence of design, but a consequence of a stupendously large multiverse where every possibility is realized, and we inevitably inhabit one of the rare, stable pockets that can support complexity. It transforms the problem from a why to a where. We are not asking why the laws are so special. We are simply mapping the rare, habitable neighborhoods in an infinite and mostly inhospitable cosmic metropolis. This idea can feel unsettling, as if it removes the quest for a deeper reason, yet it also reframes our cosmic significance. Our existence becomes a remarkable data point, proof that within the infinite chaos of possibilities, islands of delicate order can and do emerge, islands where the hidden dimensions curled up in just the right way to make a world that can look back and wonder at its own unlikely existence. But the delicate balance of a habitable universe faces its ultimate test at the edge of oblivion. The black hole information paradox is a battle between our two greatest theories at the precipice of reality itself. On one side stands quantum mechanics with its sacred law that information, the complete quantum description of any system, can never be truly destroyed. It can be scrambled, hidden, or transformed, but never erased from the cosmic ledger. On the other side stands Einstein's general relativity, which describes a black hole as a region of space-time curved so severely that nothing, not even light, can escape. When matter falls in, it is lost forever to our universe, its information seemingly vanishing behind the event horizon, the point of no return. This is the paradox. Both theories are supremely successful, yet they give contradictory answers about the ultimate fate of information. The conflict suggests that something fundamental is missing from our picture, and hidden dimensions may hold the key to resolving this cosmic contradiction. One of the most promising, mind-bending solutions is known as the ER=EPR conjecture. It proposes a radical connection between two seemingly unrelated ideas. ER refers to Einstein-Rosen bridges, better known as wormholes, tunnels through the fabric of spacetime. EPR refers to the famous Einstein-Podolsky-Rosen paradox, which describes quantum entanglement, the spooky connection where two particles can instantly influence each other regardless of distance. The conjecture boldly states that these are not just metaphors for each other, they are literally the same thing. When two particles become entangled, they are not just linked by an invisible thread of information. They are, in fact, connected by a microscopic wormhole, a bridge in the higher dimensional geometry of spacetime. This wormhole is not a tunnel you could travel through, it is a geometric manifestation of the quantum link. Now apply this to the black hole paradox. When matter falls into a black hole, its information doesn't just pile up at a singularity. Instead, the conjecture suggests that the particles falling in become intricately entangled with particles of Hawking radiation, the faint glow that black holes emit due to quantum effects. This entanglement weaves a complex, ever-growing network of microscopic wormholes, stitching the interior of the black hole to the exterior radiation through hidden pathways in the geometry. The information is never inside the black hole in a traditional sense. It is encoded in this labyrinth of quantum connections, spread across the higher dimensional fabric of spacetime itself. The black hole, in this view, is not a simple pit but a tangled knot of wormhole connections, with the information preserved in the geometry of its hidden architecture. This elegant idea uses the extra-dimensional possibility of wormholes to save quantum mechanics from a fatal violation, but not all solutions are so geometrically neat. Another, more violent proposal is the black hole firewall hypothesis. It argues that to prevent information from being duplicated, which also breaks quantum rules, the event horizon cannot be the smooth, uneventful space Einstein predicted. Instead, it must be a seething wall of ultra-high-energy particles, a literal firewall that would incinerate anything crossing it. This would protect information from falling in by destroying the infalling object at the horizon, but it blatantly contradicts the principle of equivalence, a cornerstone of general relativity which states that free fall feels like floating in empty space. The existence of such a firewall is hotly debated. Could extra dimensions offer a way out, perhaps? If our universe is a brane in a higher dimensional bulk, the event horizon we perceive might be a projection of a more complex structure. The true physics of information transfer might involve processes where data is shed into the bulk or onto other branes, avoiding both the paradox of destruction and the need for a destructive firewall. The interior of the black hole might not be a point but a gateway into the higher dimensional landscape. These fierce debates show that black holes are not just cosmic vacuum cleaners, they are the ultimate laboratories for quantum gravity. Their event horizons are the sharpest scalpels, cutting to the heart of how information, space-time, and hidden dimensions are woven together into a single, coherent reality. The black hole's horizon is a crucible for reality's deepest laws, but the very fabric of space itself might be capable of an even more prolific act of creation. This brings us to the theory of cosmic inflation taken to its ultimate conclusion, a multiverse of bubble universes. The standard story of the Big Bang begins with a hot, dense, expanding fireball. But what set that expansion in motion? The theory of inflation proposes that in the first fleeting fraction of a second, the universe underwent a period of exponential, faster-than-light expansion, smoothing it out and planting the seeds for galaxies. Yet the most profound version of this idea, eternal inflation, suggests this process never truly stops. Instead, it becomes a self-replicating, eternal engine for spawning new universes. Picture the fundamental fields that fill space, the Higgs field and others, as a vast mountainous landscape. Our universe exists in a valley, a stable low-energy state we call the true vacuum. But during inflation, space is trapped in a much higher energy state, a false vacuum perched high on a plateau. This false vacuum is unstable, and it wants to decay, to roll down the hill into a lower energy state. In most regions of the inflating cosmos, this decay happens and inflation ends. That region becomes a bubble of stable space, a new universe like our own, with its own Big Bang and subsequent evolution. But here is the breathtaking twist. The process of inflation is so rapid, it expands space faster than these stable bubbles can form and merge. So while one region decays and becomes a bubble universe, the space around it continues to inflate exponentially. Within that still inflating space, more quantum fluctuations cause new regions to decay, spawning their own bubbles. These new bubbles are then themselves separated by eternally inflating space. The result is a never-ending fractal froth of bubble universes, each pinning off from the inflating background like bubbles forming in an endlessly boiling pot. Each of these bubbles is a complete, separate cosmos, potentially with its own unique set of physical laws. When the inflation field decays in a particular region, it settles into one of the many possible low-energy states dictated by the underlying theory, like string theory's vast landscape. This means each bubble universe could have a different Calabi-Yau manifold, different compactified dimensions, and thus different fundamental constants and particles. In one bubble, gravity might be strong and stars are tiny and fleeting. In another, electromagnetism might be weak, preventing complex chemistry. Our entire observable cosmos is just one such bubble, one outcome in an infinite cosmic lottery where the laws of physics are not universal but local. These bubbles are not floating in a pre-existing space we can point to. They are domains within a higher dimensional meta-universe, the eternally inflating false vacuum itself. We cannot see outside our bubble because its boundary is expanding at nearly the speed of light, and the space between bubbles is itself inflating even faster, putting them forever out of reach. But could we ever detect evidence of our bubble's lonely existence in this infinite foam, perhaps through a cosmic scar? If, during the chaotic early moments, our bubble universe collided or grazed another bubble as both were forming, the impact would have sent colossal shockwaves rippling through the primordial plasma of each cosmos. Such a titanic event would leave a distinct, asymmetric imprint on the oldest light in the universe, the cosmic microwave background. Astronomers have searched for these telltale patterns, concentric rings of temperature variation or strange cold spots that could be bruises from a long-ago collision with another universe. While no definitive evidence has been found, the search continues, a haunting possibility that the faint afterglow of creation might hold not just the story of our beginning, but a shadow of the neighbor we never knew. This vision transforms the cosmos from a single, grand experiment into a sprawling, fecund metropolis of realities, where our familiar laws are just one set of bylaws on an infinite block. The search for a cosmic scar from another universe leads us to a question that reframes the nature of all scars, all memories, and reality itself. What if the universe we perceive is not a physical place at all, but an elaborate, hyper-realistic simulation? This is the simulation hypothesis, a modern philosophical idea that resonates eerily with concepts like the holographic principle. It suggests our three-dimensional world, with all its depth, history, and sensation, is a computational construct, a grand simulation running on a substrate of technology in a higher dimensional reality we can never access. In this view, the hidden dimensions of existence are not curled-up geometric shapes, but the very architecture of the computer running the code of our cosmos. Think of it as the ultimate virtual reality. When you play an immersive video game, your character exists in a rich, three-dimensional world with consistent physics, history, and other characters. But that world is not fundamentally real. It is a stream of data rendered according to rules, processed on hardware that exists in a reality completely outside the game's universe. The simulation hypothesis proposes we are those characters, and our universe is that simulation. Philosopher Nick Bostrom formalized this idea with a stark trilemma. He argued that at least one of three propositions must be true. First, that almost all civilizations at our level of technological advancement go extinct before becoming capable of creating realistic simulations. Second, that advanced civilizations have no interest in running such simulations. Or third, that we are almost certainly living in a simulation. The logic is based on a simple extrapolation of technological progress. If a civilization survives and continues to advance, it will eventually possess computing power so vast that running detailed simulations of entire worlds or even entire universes would be trivial. Such a civilization could run not one, but billions of simulations, each populated with conscious simulated beings. The number of simulated minds would therefore vastly outnumber the number of original biological minds. If that is the case, the odds that any given conscious being, like you or me, is one of the original beings is astronomically small. It is far more statistically likely we are one of the simulated ones. This is not proof, but a compelling probabilistic argument. Figures like Elon Musk have pointed to the rapid, inexplicable leaps in our own computing and graphics technology as a hint that we might be inside a simulation that is itself rapidly upgrading. How does this connect to the hidden dimensions of physics? The holographic principle we explored earlier provides a startling scientific parallel. It says all the information in a three-dimensional volume can be encoded on a two-dimensional boundary. This is exactly how computer graphics work today. A three-dimensional game world is not stored as a full volume of data. It is generated on the fly from a set of rules, algorithms, and textures rendered onto your two-dimensional screen. Our universe could be a vastly more sophisticated version of this, a projection from a lower dimensional source code. Furthermore, the discovery that space-time itself may be quantized, that there is a smallest possible unit of distance and time, the Planck scale, fits perfectly with the concept of a simulation. In any digital simulation, there is a finite resolution, a pixel size. The Planck length and Planck time could be the fundamental pixel size of our reality, the limit below which the simulation does not bother to render detail because no processing power is allocated to it. The laws of physics we have discovered, from gravity to quantum mechanics, would not be fundamental truths of a base reality, but simply the rules of the simulation's programming, its operating system. This idea forces us to confront profound questions about consciousness and existence. If we are in a simulation, is our free will an illusion, or is it simply a very complex algorithm? Are our memories just saved data files? And what is the purpose of the simulation? Are we someone's science project, an ancestor simulation run by our distant descendants to understand their past, or perhaps just entertainment for beings in a higher plane of existence? While the simulation hypothesis is not a physical theory with testable equations like string theory, it represents a powerful modern mythology, a framework that makes the concept of hidden layers of reality viscerally understandable. It asks us to consider that the most fundamental discovery we could make is not a new particle or dimension, but the source code of the simulation itself, a glitch in the matrix that reveals the programmer's hand. And if that is ever found, what then? The idea of a simulated reality forces us to confront the nature of the one thing experiencing it all, our own conscious awareness. This leads us to a theory so speculative it blurs the line between physics and philosophy, the notion that consciousness itself may be a higher dimensional phenomenon. What if your thoughts, your feelings, your sense of self are not simply chemical reactions confined within your skull? What if the brain is not a generator of consciousness but a receiver, a complex antenna tuned to a signal originating from a realm beyond our three-dimensional perception? This is not science fiction, but a serious proposal from some corners of theoretical physics and philosophy, suggesting that the hidden dimensions we have been exploring could be the true substrate of subjective experience. One framework supporting this idea is integrated information theory. It attempts to mathematically measure consciousness by quantifying how interconnected and differentiated a system is, how much information it integrates into a unified whole. Under this theory, consciousness is not an on-off switch but a spectrum. A human brain, with its trillions of intricate neural connections, possesses a high degree of integrated information, resulting in rich conscious experience. But the theory does not limit consciousness to biological wetware. In principle, any system with sufficient complexity and integration could possess some degree of consciousness, from a sophisticated computer network to perhaps the universe itself. This is where the hidden dimensions come in. If the fundamental fabric of reality is a vast, interconnected network of information in a higher dimensional space, as suggested by theories like the holographic principle, then the cosmos itself could have an unimaginably vast degree of integrated information. Our individual brains, with their three-dimensional neural architecture, might be localized knots or interfaces within this cosmic network, each granting access to a tiny fragment of a universal consciousness. We are not separate islands of awareness, but whirlpools in a much deeper, higher dimensional stream of experience. This connects to an ancient philosophical idea updated for modern physics, panpsychism. Panpsychism proposes that consciousness is a fundamental property of the universe, like mass or charge. It suggests that all matter, at some basic level, has an elemental form of experience or proto-consciousness. An electron might have a minuscule, unimaginable flicker of raw feeling. These flickers, when combined in the staggeringly complex integrated system of a human brain, give rise to the rich tapestry of thought, emotion, and sensation we know. But if consciousness is fundamental, where does it reside? The hidden, compactified dimensions of string theory or the warped bulk of brain worlds could provide an answer. Perhaps these extra dimensions are not just geometric spaces for strings to vibrate, but are themselves imbued with this fundamental property of awareness. Our three-dimensional brains, evolving within this higher dimensional reality, could have developed the specific structures necessary to resonate with, filter, and interpret this underlying conscious field, much like a radio tunes into specific frequencies from the electromagnetic spectrum. We do not create the broadcast, we simply decode it. This perspective turns the hard problem of consciousness, the question of how physical processes give rise to subjective experience, on its head. It suggests the problem is hard because we are looking in the wrong place, in our limited three-dimensional slice of reality. The feeling of the color red, the taste of chocolate, the ache of sadness, these qualia might be higher dimensional phenomena that our brains translate into the language of three-dimensional perception. It is a breathtaking, if unproven, vision where the most intimate aspect of our existence, our inner world, becomes a direct window into the deepest architecture of the cosmos. If true, then every moment of awareness is not just a private event, but a fleeting touch with the hidden dimensions that shape all of reality. We are so accustomed to time's relentless flow that it feels like the most fundamental rule of existence. Yet Einstein's theory of relativity shattered this intuitive view, merging time with space into a single, four-dimensional fabric called spacetime. This fusion leads to one of the most profound and humbling ideas in all of physics, the block universe theory. In this view, the past, present, and future are not sequential. They all exist permanently and equally, laid out together in a vast four-dimensional block. Picture a loaf of bread. The entire loaf represents all of space-time, from the Big Bang to the far future. A single slice of that loaf represents the universe at one specific moment, what we call the present. As we experience life, it is not that the loaf is being baked slice by slice. Instead, our consciousness is simply moving along the loaf, illuminating one slice after another. The loaf is complete, a static sculpture. Your birth is in one slice, your reading of these words is in another slice further along, and your distant future is in a slice waiting ahead. This means that from a higher dimensional perspective outside the block, everything that has ever happened or will happen is already there, fixed in the geometry. The feeling of time flowing, of the future being open and the past gone, is an illusion of our consciousness, a feature of how we are embedded within the block. We are like a reader moving through a book page by page, even though all the pages already exist, bound together. This is not science fiction. It is the direct implication of Einstein's equations, where time is relative and simultaneity is not absolute. But if time is just another dimension in the block, could it be more complex than a single, simple line? Some theorists propose that time itself might have hidden dimensions. We are familiar with moving forward and backward in time, at least in thought. But what if you could move sideways in time? This is the concept of multiple temporal dimensions. In a universe with 2 dimensions of time, the fabric of reality would be described by 6 dimensions, 4 of space and 2 of time. This is nearly impossible for our minds to visualize, but it would radically alter the nature of possibility and causality. In our one-dimensional time, events are points on a line, and cause must always precede effect. With 2 times, events become points on a plane. You could travel from one event to another along many different paths, some of which might loop back in what we would call the past without ever violating local causality. It would allow for a kind of temporal freedom that makes our idea of a fixed timeline seem quaint. The laws of physics in such a universe would be extraordinarily complex, likely allowing for closed time like curves, essentially natural time loops woven into the geometry of reality. An even more radical idea strips time of its fundamental status entirely. Perhaps time is not a primary dimension at all, but an emergent property, a collective illusion that arises from a more basic, timeless reality. This is like the way temperature emerges from the frantic motion of countless molecules, a useful concept that doesn't exist for a single atom. In theories of quantum gravity, some approaches suggest that the universe at its most fundamental level is static and changeless. The wave function of the universe, a mathematical object describing all possibilities, might simply be with no external time parameter. The flow of time we experience could then emerge from the intricate correlations between parts within this frozen whole. Think of a completed, intricate jigsaw puzzle. The puzzle itself is static, but if you could only see it through a moving, narrow spotlight, you would perceive a sequence of connected images, a story unfolding. Our conscious observation of the universe, locked within its structure, might be that moving spotlight, creating the sensation of change and duration from a timeless substrate. This suggests that the hidden dimensions we seek might not all be spatial. The true architecture of existence could include temporal dimensions beyond our perception, or it might have no time at all at its foundation, with time being a story we tell ourselves to make sense of our journey through an eternal, higher dimensional block. The block universe presents a timeless landscape, but within that frozen geometry, physicists search for a different kind of perfection, a hidden harmony that may orchestrate all of reality. This quest is for the God equation, a term that captures the dream of a single, supremely elegant mathematical principle from which every force and particle emerges. At the heart of this search lies a concept of breathtaking beauty, symmetry. Not the simple symmetry of a butterfly's wings, but a deep, abstract, and multidimensional symmetry that may be the true language of the cosmos. These are not just patterns we see, they are the fundamental transformations under which the laws of physics remain unchanged, the invisible gears that make the universe tick. The most promising candidates for this ultimate symmetry are described by exotic mathematical structures known as Lie groups, with names like SU5, SO10, and one of the most magnificent of all, E8. The E8 group is a monster of symmetry, a 248-dimensional mathematical object of stunning complexity and order. It is not a shape in our space, but a pattern of relationships, a cosmic choreography with 248 dancers moving in perfect, interdependent harmony. Visualizing E8 is a challenge for our three-dimensional minds, but its shadow can be seen in intricate, snowflake-like diagrams called root systems, vast starry patterns of connections that hint at an underlying architecture of immense sophistication. The tantalizing theory is that this perfect E8 symmetry, or something like it, is the true, unified state of all forces and matter, but we do not see this perfection in our world. Our universe appears messy and broken apart, with four distinct forces and a zoo of seemingly unrelated particles. Why? The answer may be that this sublime symmetry can only exist fully in a space with more dimensions than we experience. In a higher dimensional arena, perhaps 10 or 11 dimensions as string theory suggests, the equations could achieve a state of perfect, unbroken symmetry. All forces would be one force, all particles would be different vibrations of a single entity, all described by the elegant geometry of E8. Our three-dimensional reality, then, is the result of a cosmic cooling, a phase transition. As the early universe expanded and cooled, it is theorized that this perfect symmetry shattered, like a pane of glass cracking as it cools too quickly. The single, unified force splintered into the four we know: gravity, electromagnetism, and the strong and weak nuclear forces. The particles we see, like electrons and quarks, are the fragmented pieces of that original, symmetrical whole. In this view, our entire cosmos is a kind of shadow, a broken reflection cast by a perfect, higher-dimensional object. We are living in the aftermath of the break, seeing only the jagged fragments of a beautiful vase. The messy parameters of our world, the different strengths of forces, and the seemingly random masses of particles are not fundamental. They are accidental fossils, frozen remnants of how the symmetry broke as the hidden dimensions curled up into their specific Calabi-Yau shape. Finding the God equation, therefore, is not about writing an equation for our fractured world. It is about discovering the pristine, symmetrical equation that governs the higher dimensional reality, and then understanding the precise mechanism of the breaking. Our universe would then be understood not as it is, but as a particular solution, one specific way the perfect symmetry could have cracked. This transforms the goal of physics. We are not just cataloging the fragments on the floor, we are trying to reconstruct the design of the original, flawless sculpture, a sculpture that may only be whole in the silent, hidden dimensions we can never directly perceive. The perfect symmetry of E8 may have broken, but its fragments still whisper to each other across the cosmos in a phenomenon that defies all intuition. Quantum entanglement is the universe's most intimate secret, a ghostly connection where two particles, once linked, remain in instantaneous communication regardless of the distance separating them. Change the spin of one entangled particle here, and its partner, even if it's on the other side of a galaxy, instantly reflects that change. Einstein famously derided this as spooky action at a distance, a violation of the cosmic speed limit set by light. For decades, this remained a profound puzzle, a quantum weirdness that seemed disconnected from the geometry of gravity and spacetime. But a revolutionary idea is stitching these two great mysteries together, suggesting that entanglement is not a disembodied signal, but a physical bridge woven from the very fabric of reality. This is the ER equals EPR conjecture, and it is one of the most profound unifications in modern theoretical physics. The equation is simple in its symbolism but staggering in its implication. ER stands for Einstein-Rosen bridges, the formal name for wormholes, tunnels through the geometry of spacetime that could, in theory, connect distant locations. EPR stands for the Einstein-Podolsky-Rosen paradox, the very thought experiment that highlighted the bizarre nature of quantum entanglement. The conjecture boldly states that these are not just analogous ideas, they are mathematically and physically the same thing. When two particles become entangled, they are not linked by some invisible, magical force traveling faster than light. Instead, they are literally connected by a microscopic wormhole, a tunnel in the higher dimensional geometry of the universe. This wormhole is not a tunnel you could ever travel through. It is fantastically small, unstable, and exists at a scale far below anything we can probe. But it is a real geometric feature, a shortcut through the hidden dimensions that makes the particles effectively adjacent in a higher dimensional space, even while they appear vastly separated in our three-dimensional view. To understand this, imagine 2 points drawn on a sheet of paper far apart. In the flat, two-dimensional reality of the paper, the shortest distance between them is a straight line. But if you allow the paper to curve through a third, hidden dimension, you could fold it so the 2 points touch. The wormhole is that fold, creating a new, shorter path through the higher dimension. Quantum entanglement is the physical manifestation of that fold. The particles are not communicating faster than light. They are simply next-door neighbors in the folded geometry of a higher dimensional bulk. This idea transforms our understanding of the cosmos's architecture. It suggests that the fabric of spacetime itself, the smooth continuum we move through, is not fundamental. It is an emergent tapestry woven from countless threads of quantum entanglement. Every entangled pair, every quantum connection, is adding a stitch to the geometric structure of reality. In this view, empty space is not truly empty. It is a dense, vibrant network of these microscopic wormholes, a quantum foam of connections linking every point to every other point through higher dimensional shortcuts. This provides a breathtakingly elegant solution to the black hole information paradox we explored earlier. Information that falls into a black hole doesn't vanish. It becomes scrambled and entangled with the Hawking radiation the black hole emits. According to ER equals EPR, that entanglement automatically creates a web of wormhole connections between the black hole's interior and the outgoing radiation. The information is never lost. It is preserved in the complex geometry of these bridges, intricately woven into the hidden dimensions. The conjecture takes us even further. It hints that if you could somehow amplify and stabilize these natural, microscopic wormholes, perhaps with colossal amounts of energy or exotic matter, you might be able to create a traversable bridge, a true gateway. But more fundamentally, it tells us that the quantum and the geometric are two sides of the same coin. The spooky action that troubled Einstein is not an abstract signal. It is the quiet hum of the universe's hidden geometry, a constant reminder that what we perceive as separate is often connected in directions we cannot see. Even the ghostly connections of quantum entanglement cannot explain one of cosmology's most stubborn and unsettling mysteries, a strange alignment in the universe's first light that seems to point a finger at a fundamental direction in the void. This is the so-called axis of evil, a name that perfectly captures its unnerving challenge to our most cherished cosmological principle. That principle is the Copernican principle, the idea that our place in the universe is not special. The universe, we believe, should look roughly the same in all directions, homogeneous and isotropic on the largest scales. Yet, when scientists analyze the most ancient snapshot we have, the cosmic microwave background radiation, they find a series of odd, large-scale patterns that seem to whisper otherwise. These are not the tiny temperature fluctuations that seeded galaxies, but broader alignments, a strange clustering of hot and cold spots that appears to create a kind of cosmic equator and axis running through space. It is as if the universe has a subtle tilt, a preferred direction imprinted at its birth. The name Axis of Evil was coined half in jest, but the puzzle it represents is deadly serious. Could this alignment be a statistical fluke, a trick of how we map the sky? Perhaps, but its persistence across multiple satellite missions has kept the possibility alive that it is a real feature, a fossil from a time before time. One radical explanation ties directly to the architecture of hidden dimensions. If our universe is a three-dimensional brane floating in a higher dimensional bulk, as brane world theories suggest, then our entire cosmic island could be in motion. Just as a sheet of paper can drift through the air, our brane could be slowly drifting or rotating through the bulk. This motion would leave an imprint on the early universe. The physics of the Big Bang, as seen from a moving frame, would not be perfectly uniform in all directions. It would have a subtle dipole, a kind of Doppler effect for the entire cosmos, which could manifest as these large-scale alignments in the microwave background. In this view, the axis of evil is not an axis of the universe itself, but the wake of our universe's journey through a hidden sea. We are detecting the ghost of our own motion through a dimension we cannot perceive. Another, even more profound possibility is that this alignment is a scar from before our Big Bang. If the cosmos is cyclic, born from the collision of branes, or if it emerged from a pre-existing structure, that parent geometry could have imposed a directionality, a spin or a warp that our newborn universe inherited. The axis of evil would then be a cosmic birthmark, a clue to a larger reality that existed before our clock started ticking. While most cosmologists remain skeptical, preferring to attribute the signal to unknown instrumental effects or complex foreground noise, its tantalizing presence endures. It serves as a haunting reminder that our most fundamental assumptions about cosmic uniformity are ultimately assumptions. The universe may yet have a quiet preference, a whisper of directionality written in its oldest light, pointing not just across space, but perhaps into the very dimensions that cradle our reality. The unsettling whisper of a cosmic axis leads us to a far louder mystery, a ghost that shapes the fate of galaxies yet refuses to be seen. For decades, dark matter has been the universe's most dominant and frustrating secret, a form of matter that exerts a powerful gravitational pull but emits no light, no radiation, nothing we can directly touch. We know it's there because galaxies spin too fast to hold together without its invisible glue, and vast cosmic structures would never have formed without its gravitational scaffolding. But what is it? The leading answer has been a new, exotic particle, something like a WIMP, a weakly interacting massive particle that fills our universe but barely notices we exist. Yet after decades of searching in giant underground detectors and powerful particle colliders, we have found nothing. This profound silence forces us to ask a radical question. What if we are looking in the wrong place entirely? What if dark matter is not hiding in our dimension, but is right next to us in another? This brings us to a breathtaking possibility within brane world cosmology. Imagine our three-dimensional universe is a membrane, a vast sheet, floating in a higher dimensional space called the bulk. Now imagine another brane, a parallel universe, floating extremely close to ours in that hidden direction. The distance between these two branes could be minuscule, perhaps even at the microscopic scale of the extra dimensions themselves. On that neighboring brane, the story of cosmic evolution could have unfolded very much like our own. Stars ignited, galaxies swirled, and black holes formed, all made from ordinary atoms and forces. From the perspective of a being on that brane, their universe is bright and full of matter. But from our perspective, trapped on our own membrane, we cannot see any of their light or interact with any of their particles. The forces of electromagnetism and the nuclear forces are stuck to their own brane, just as ours are stuck to ours. There is one exception, gravity. As we have explored, gravity can leak off a brane and seep into the bulk. So, the immense gravitational pull of all those stars, gas clouds, and black holes on the neighboring brane would bleed through the tiny gap in the higher dimensional bulk and into our universe. We would feel that gravity as a powerful, invisible presence tugging on our galaxies and bending the light from distant stars, yet we would see absolutely nothing causing it. In this model, dark matter is not an exotic particle. It is simply ordinary matter living an ordinary life in a parallel reality that happens to be gravitationally coupled to our own. Its particles are protons, neutrons, and electrons, but they are not our protons, neutrons, and electrons. They belong to another sheet of existence. This elegantly explains why dark matter seems to clump in massive halos around galaxies, exactly where you would expect the gravity of a parallel galaxy to be felt. It also explains why it is so stubbornly non-interactive with our light and matter beyond gravity. There is no need for a new, undiscovered particle with just the right weird properties. The mystery is solved by geography, not particle physics. We are feeling the weight of a shadow cosmos, a cosmic neighbor whose lights are forever off in our dimension, but whose gravitational presence is the hidden hand guiding the rotation of every star in our night sky. That shadow cosmos, its gravity pressing on our own, exists in a higher dimensional stillness. But what if that stillness was once shattered by a cataclysm that birthed everything we know? The collision of branes is not just a theoretical curiosity, it is a detailed physical account of creation. In the ekpyrotic and cyclic models, the universe begins not with a singularity but with a near miss. Picture two immense, flat, three-dimensional membranes, each potentially infinite in extent, floating parallel to each other in the higher dimensional bulk. They are not empty in a true sense, but they are cold, dark, and nearly featureless, existing in a state of low energy. These two cosmic sheets are drawn together by the faintest of forces, perhaps the gentle pull of gravity acting through the bulk or a subtle field that attracts one brane to the other. Their approach is not a head-on crash, but a slow, deliberate convergence. They move with a cosmic patience, taking perhaps trillions of years to close the microscopic gap that separates them in the hidden dimension. This long, drawn-out approach is crucial, as it stretches and flattens any wrinkles or imperfections on the branes, naturally explaining the stunning uniformity we see in the cosmic microwave background without needing a period of rapid inflation. There is no mysterious inflattened field here, just the slow, inevitable geometry of attraction. Then they meet. The collision is not a chaotic, splattering impact. Because the branes are nearly perfectly parallel and flat, they collide uniformly across their entire infinite surfaces all at once. At the moment of contact, the immense kinetic energy of their motion, built up over eons, is converted violently into heat and matter. The cold, dark emptiness of the pre-collision brane is transformed in an instant into a searing, dense ocean of fundamental particles, a quark-gluon plasma of unimaginable temperature. This is our Big Bang. It is not an explosion from a point, but a fire ignited simultaneously everywhere across a three-dimensional canvas. The universe is born hot and expanding because the branes do not stick together. They act like elastic sheets, colliding and then rebounding, springing apart. As they separate, the space within our brane, now filled with that primordial fire, stretches and cools, allowing particles to coalesce into atoms, then stars, and finally galaxies. All the structure we see is the aftermath of that single, universe-spanning collision. But the story does not end with the rebound. This is where the model becomes truly cyclic. After the branes fly apart, the attractive force between them remains. Their outward motion slows, halts, and over another eternity reverses. They are drawn together once more, destined to collide again and trigger a new Big Bang, a new universe on the surface of the brane. In this view, our cosmos is just one episode in an endless, rhythmic saga of creation and separation, a cosmic heartbeat echoing through the bulk. This breathtaking narrative makes a specific, testable prediction. Such a violent, planar collision would not be perfectly smooth. Tiny quantum ripples on the branes just before impact would be amplified into vast, stretching distortions in spacetime itself. These distortions would generate a unique background of gravitational waves, ripples in the fabric of reality with a very distinct pattern across different frequencies. Unlike the chaotic gravitational waves from merging black holes, this signal would be a primordial hum, a fossil vibration from the very moment of creation. Future observatories like the proposed space-based laser interferometer known as the Laser Interferometer Space Antenna, or LISA, are designed to listen for such whispers from the early universe. If the ekpyrotic model is correct, LISA might one day tune into this specific gravitational wave signature, a direct echo of the moment our brain struck its twin. It would be the first tangible evidence that our universe was born not from a mysterious singularity, but from a shattering impact in a hidden dimension, an impact that may happen again and again forever. But that eternal rhythm of creation carries a silent, chilling possibility. Our universe might not be waiting for the next grand collision, but for a quiet, internal collapse from within. This is the harrowing concept of vacuum decay, a cosmic doomsday scenario written into the very fabric of empty space. To understand it, we must revisit the idea of the cosmic landscape, that vast terrain of possible universes defined by the shape of hidden dimensions. Each valley in this landscape represents a stable or semi-stable set of physical laws, a particular vacuum state. Our universe sits in one such valley, but it may not be at the very bottom. It might be perched in a metastable state, a false vacuum that seems solid and permanent, but is actually resting on a precarious shelf. Given enough time or the right quantum nudge, it could suddenly fall into a deeper, more stable valley, a true vacuum with completely different laws of physics. This transition would not be a slow change. It would happen through a process called quantum tunneling. Imagine a ball rolling in a valley, but separated from a much deeper, lower valley by a tall, thin hill. Classically, the ball lacks the energy to roll over the hill, but in the quantum world, particles and fields can sometimes cheat. They can tunnel through the barrier, appearing on the other side as if by magic. In the cosmic landscape, the Higgs field, which gives particles their mass, could be that ball. Somewhere in the universe, at a random point in space, a tiny bubble of this new, true vacuum could spontaneously nucleate via quantum tunneling. The moment this bubble forms, the physics inside it is irrevocably altered. The fundamental constants change, the strength of forces shifts, atoms, chemistry, and the very rules that allow matter to hold together cease to exist. This bubble would then expand in all directions at the speed of light, its spherical wall a boundary of annihilation. As it expands, it rewrites reality in its wake, converting the old, metastable vacuum into the new, true one. From our perspective, there would be no warning. One moment, the universe is normal. The next, an invisible wall of transformation sweeps through our galaxy, our solar system, our planet. Since it travels at light speed, we could not see it coming. Everything we know, every structure from galaxies to DNA, would simply cease to be, not in an explosion, but in a silent reconfiguration of the laws of nature themselves. The universe would continue, but it would be a different universe, one almost certainly incapable of supporting any complexity, let alone life. This terrifying process is framed entirely within the higher dimensional landscape. Our bubble universe is not just a region of space, it is a specific valley in that abstract terrain. The decay is the universe slipping from one valley to another, a catastrophic landslide in the geometry of the hidden dimensions. The stability of our world, then, depends on the shape of those curled-up Calabi-Yau manifolds and the depth of our particular valley. Some calculations suggest our vacuum might be metastable, with an average lifetime far longer than the current age of the universe, but not infinite. This means the doomsday clock is ticking on a scale of billions or trillions of years, a time span so vast it feels like eternity. Yet it introduces a profound fragility to existence. We are living in a cosmic edifice that is not necessarily permanent, but merely durable, a temporary configuration in an endless landscape of possibilities, where a single quantum event could, at any moment, erase everything in a sphere of light that grows to consume the cosmos. The silent fragility of our vacuum hints at a cosmos built on shifting mathematical possibilities. This leads us to a theory so absolute it dissolves the boundary between the abstract and the real. The mathematical universe hypothesis, championed by physicist Max Tegmark, proposes a breathtaking and final answer. It states that every single mathematical structure that is logically consistent exists as a physical reality. Our universe, with its 3 dimensions of space and 1 of time, is not a unique creation. It is simply one specific mathematical structure among an infinite, timeless ensemble. In this ultimate multiverse, a structure describing 4-dimensional spacetime with quantum fields exists right alongside a structure describing an 8-dimensional crystal lattice, or a universe built entirely on fractal geometry. If the equations are coherent, that universe is real. This is not saying mathematics describes the universe well. It is saying the universe is mathematics. We are not discovering pre-existing physical laws. We are uncovering the properties of the particular mathematical object we inhabit. In this radical view, dimensions lose their mystical quality. They are not curled up loops or warped bulk spaces waiting to be discovered. They are simply mathematical parameters, numbers in an equation defining a structure. The hidden dimensions we have been exploring throughout this journey are simply those parameters that are set to 0 or are otherwise not instantiated in our specific substructure. They are part of a larger mathematical possibility space that our particular cosmic address does not utilize. To grasp this, think of a simple equation like that for a circle. The equation x squared plus y squared equals r squared defines an infinite set of points, a perfect 2-dimensional shape. In the mathematical universe hypothesis, that circle isn't just an idea. It is a physical, 2-dimensional universe where the particles are the points satisfying the equation, and the laws of physics are the rules of Euclidean geometry. Our universe is just a vastly more complicated equation with far more variables and parameters. Tegmark arranges this into a 4-level multiverse. Level 1 is simply a continuation of our own space, regions so far away we cannot see them. Level 2 contains universes with different physical constants, like those born from eternal inflation. Level 3 is the quantum many worlds where every possibility branches. But Level 4 is the final frontier, the set of all mathematical structures. This is where the theory becomes profoundly philosophical. It answers the age-old question of why mathematics is so unreasonably effective in describing nature. The answer is simple. We are doing nothing more than exploring the innate properties of our own mathematical home. It also confronts the fine-tuning problem with ultimate finality. In an infinite ensemble where every possible mathematical structure exists, it is no surprise that one exists with constants allowing for stars, planets, and conscious observers. We could not find ourselves in a structure incompatible with our own existence. The theory is austere and elegant, removing the need for any external creator or unexplained physical substrate. Reality just is the timeless, eternal landscape of mathematical truth, but it also presents a dizzying, almost alien perspective. Your consciousness, your memories, the feeling of the wind on your face are all part of a complex computation within a specific mathematical object. The warmth of a star, the chill of space, are not emergent properties of a physical substance, but logical consequences of a particular set of equations playing themselves out. This begs a haunting question: if we are patterns in a mathematical structure, who or what is doing the perceiving? The theory suggests that self-aware substructures like us can exist within these mathematical systems, capable of observing and modeling the very rules that define them. We are the universe's way of understanding its own equations. While this hypothesis is currently untestable in any conventional sense, it represents the logical endpoint of a journey that began with wondering about curled-up dimensions. It pushes the idea of hidden realities to its absolute limit, proposing that the most fundamental layer of existence isn't made of strings, branes, or quantum fields, but of pure, abstract mathematical relationships. In such a cosmos, the search for hidden dimensions transforms from a hunt for unseen geometry into a quest to fully decipher the specific, magnificent equation we call home. The austere beauty of pure mathematical structures finds a surprising echo in a radically different approach to reality's fabric. While string theory weaves the cosmos from vibrating loops in hidden dimensions, another school of thought asks a more fundamental question. What if spacetime itself has no pre-existing geometry? What if dimensions are not hidden but built from scratch? This is the causal dynamical triangulations approach, a powerful contender in the quest for quantum gravity that constructs the universe from the ground up, one tiny geometric piece at a time. Imagine you are tasked with building a smooth, curved surface like a dome, but you are only allowed to use small, flat triangles. You start gluing them together, edge to edge. With just a few triangles, the shape is jagged and fragmented. But as you add millions, even billions of identical triangles, following specific rules for how they connect, something remarkable happens. The collective structure begins to approximate a smooth, continuous curve. The dome emerges not from the triangles themselves, but from their vast, interconnected network. Causal dynamical triangulations applies this logic to the fabric of reality. It proposes that at the unimaginably small Planck scale, spacetime is not a smooth continuum. It is a chaotic, ever-changing froth of possibility. To make sense of it, theorists break this foam into its most basic building blocks. In this approach, the fundamental units are not strings or branes, but incredibly tiny, simple pieces of geometry, specifically four-dimensional triangular blocks called simplices. Think of them as the elementary Lego bricks of spacetime. The theory then performs a breathtaking mathematical operation. It considers every single possible way these tiny geometric blocks can be glued together to form a larger structure, summing over all these potential configurations. This is not a single, static architecture, but a superposition of every possible spacetime history, a quantum mechanical sum over all possible paths the universe could have taken to reach its current state. But there is a crucial, guiding rule woven into this cosmic construction kit: causality. The connections between these blocks must respect the flow of time, ensuring cause always precedes effect. This simple constraint, this demand for an orderly sequence of events, acts as a powerful organizing principle. Without it, the sum over all configurations would produce a meaningless, jumbled mess, a universe with no coherent structure or dimensionality. With it, something magnificent emerges from the chaos. When physicists run supercomputer simulations of this process, starting with a soup of these geometric building blocks and letting them assemble according to the rules of quantum mechanics and causality, a stable, large-scale structure consistently crystallizes out. That structure is our familiar four-dimensional spacetime, with 3 dimensions of space and 1 of time. The smooth, continuous universe we experience is a collective illusion, a statistical average born from the frenetic interactions of countless microscopic geometric pieces. But the most stunning prediction lies at the very smallest scales. As the simulation probes the fabric of reality at distances approaching the Planck length, the effective dimensionality of the universe does not remain 4. It changes. The calculations reveal that spacetime undergoes a dimensional reduction. At these extreme scales, the chaotic quantum fluctuations are so violent that the neat, 4-dimensional order breaks down. The universe effectively becomes 2-dimensional. It is as if when you zoom in impossibly close on what seems like a smooth, 3-dimensional volume, you discover it is actually woven from a complex, mesh-like fabric that behaves more like a surface. This is not because there are literal, hidden two-dimensional sheets, but because the quantum geometric building blocks connect in such a wildly fluctuating way that the concept of volume loses its meaning. The number of directions you can move, the very degrees of freedom, become those of a two-dimensional world. This paints a dynamic, emergent picture of dimensions. In this view, dimensionality is not a fixed, inherent property of the cosmos. It is a phase of matter like ice or steam that depends on the scale at which you examine it. At the human and cosmic scale, space-time is in a four-dimensional phase. At the quantum gravitational scale, it transitions into a two-dimensional phase. Dimensions are not hidden, they are behaviors, collective properties that arise from the underlying dance of simple geometric parts. This offers a profound alternative to the idea of extra, curled-up dimensions. Here, the mystery is not where the other dimensions are, but why the four we experience emerge so robustly from the quantum noise. The answer lies in the silent, relentless enforcement of causality, a rule so basic it stitches the fragments of possibility into a world where time flows forward and space holds its shape, a world stable enough for us to stand in and wonder at its origins. The silent, mathematical architecture of space-time must at some point leave a trace we can measure. Our journey through theories now turns to the tangible, to the experimental hunt for the fingerprints of hidden dimensions. This is the phenomenology of extra dimensions, the search for their subtle, physical signatures in our world. If these realms exist, however curled up or warped, they must whisper to us through faint deviations in the laws we know. Scientists are listening with exquisitely sensitive instruments, probing reality at its most extreme edges for the slightest tremor of something more. One of the most direct tests involves the most familiar of forces, gravity. Sir Isaac Newton, and later refined by Einstein, told us that gravity weakens with the square of the distance. This inverse square law is a cornerstone of physics, but if there are extra spatial dimensions, especially large ones as suggested by brane world models, this law should break down at very small distances. Why imagine gravity as a force that spreads out? In our three-dimensional world, it dilutes as it spreads over the surface of an ever-growing sphere. But if gravity can also leak into a hidden, fourth spatial dimension, it would have more room to spread, weakening faster than the inverse square law predicts. At macroscopic distances, this effect is negligible. The extra dimension is too far away for much leakage. But at microscopic scales below a millimeter, the force could have a shortcut into the bulk, causing a detectable deviation. This has led to a fascinating frontier of physics, tabletop experiments that measure the gravitational attraction between exquisitely crafted masses separated by tiny gaps. Researchers use delicate torsion balances, essentially modern versions of the instrument Henry Cavendish used to weigh the Earth, but operating at distances smaller than the width of a human hair. They are searching for a sudden, unexpected strengthening or weakening of gravity as the masses are brought incredibly close together. Finding such a deviation would be a monumental discovery, a direct signal that gravity is exploring realms beyond our perception. Another hunting ground is the world of the unimaginably small and energetic, deep within the Large Hadron Collider. When protons are smashed together at nearly the speed of light, they release a staggering amount of energy which condenses into a shower of new particles. The collider's detectors act as cosmic cameras, capturing the aftermath of these microbangs. If extra dimensions exist, they could provide an escape route. In a collision, one of the products could be a graviton, the particle that mediates gravity. In our brane world scenario, that graviton, unlike other particles, could promptly vanish off our brain and into the bulk, carrying its energy with it. From the perspective of the detector, this would look like a glaring case of missing energy. The books would not balance. The total energy and momentum measured after the collision would be less than what was put in, with no visible particle to account for the loss. The LHC experiments are meticulously searching for these imbalanced events, sifting through billions of collisions for the telltale signature of energy slipping silently into a hidden dimension. While no definitive signal has been found, the search continues to constrain the possible size and nature of these extra realms, telling us where they cannot be. Finally, the cosmos itself may be broadcasting evidence through the ripples in spacetime known as gravitational waves. The mergers of black holes and neutron stars detected by observatories like LIGO and Virgo send precise tremors through the fabric of reality. Hidden dimensions could alter this music in specific ways. For instance, if gravity propagates through a warped bulk, the gravitons carrying the waves might take slightly different paths through the higher dimensional geometry, arriving at our detectors at subtly different times. This could create faint echoes in the gravitational wave signal, a repeating chirp following the main event. Furthermore, exotic objects predicted by higher dimensional theories, like microscopic black holes that evaporate instantly or cosmic strings that vibrate in compactified directions, would produce unique gravitational wave fingerprints. As our detectors become more sensitive, they will listen not just for the crashes of massive objects, but for these higher dimensional harmonics, the ghostly reverberations of a universe with more room than we can see. The hunt is on across scales, from tabletops to particle colliders to the waves from colliding stars. Each null result narrows the possibilities, and each potential anomaly sends a thrill through the scientific community. We are no longer just imagining hidden dimensions, we are actively stalking them, designing experiments to force them out of hiding. The next great discovery in physics might not be a new particle in a detector, but a tiny, persistent anomaly in the pull between two gold spheres, or a whisper of missing energy in Geneva, telling us that our reality is just a slice of something infinitely grander. This relentless experimental hunt is driven by a question that has haunted humanity since we first looked at the stars. What if we are profoundly, fundamentally wrong about the nature of our own existence? The possibility of hidden dimensions is not merely a technical puzzle for physicists. It is a philosophical earthquake that shakes the very foundations of how we see ourselves. For centuries, we have operated under an unspoken assumption of centrality, the anthropocentric view that our human perspective is the privileged lens through which reality is revealed. Our senses define the world, our logic maps its rules, and our consciousness stands at the pinnacle of its complexity. Yet every theory of hidden realms whispers the same unsettling truth: we are not central. We are incidental. We are creatures evolved to survive in a very specific, narrow band of a reality that is almost entirely concealed from us. We are like deep-sea fish, born and living in perpetual darkness, unaware of the concept of a sunlit sky, of mountains, of a universe of color and air. Our entire perception of existence is built from data filtered through biological sensors tuned only to a sliver of the electromagnetic spectrum, interpreted by a brain that evolved to avoid predators and find food, not to comprehend the geometry of 10-dimensional space. This realization dismantles our trust in sensory perception. The solidity of the ground beneath your feet, the vastness of the night sky, the very three-dimensional room you are in, all of this could be a magnificent illusion, a user interface projected for beings who can only process a limited set of inputs. We are not seeing reality, we are seeing a dashboard, a simplified representation built from shadows and echoes of something infinitely more complex. This idea is ancient. Over 2,000 years ago, the philosopher Plato presented his allegory of the cave. He asked us to imagine prisoners chained from birth in a dark cavern facing a blank wall. Behind them, a fire burns, and between the fire and the prisoners, people carry objects that cast shadows on the wall. For the prisoners, these shadows are the only reality they have ever known. They name them, discuss them, and believe them to be solid and complete. If one prisoner were freed and dragged out of the cave into the blinding sunlight, he would at first be pained and confused by the true, three-dimensional objects casting the shadows. But eventually, he would understand the profound depth of his previous ignorance. He would see color, dimension, and the source of the light itself. If he returned to the cave to tell the others, they would not believe him. They would think his journey had ruined his sight and his mind. Our current scientific journey out of the cave is that painful, dazzling ascent. The curled-up dimensions of string theory, the holographic projection, the brane worlds floating in the bulk, these are the true objects behind the shadows we have been staring at all along. The particles we catalogue, the forces we measure, the very space-time we move through, these are the flickering images on the wall. The fire is the higher dimensional geometry, and the sun is the ultimate, perhaps mathematical, source of all structure. This connection between ancient philosophy and cutting-edge physics is not a coincidence. It is evidence of a timeless human drive, an insatiable need to poke at the edges of our perception, to suspect there is more. That drive built civilizations, launched telescopes, and now builds particle colliders. We are the species that is never content with the dashboard. We must try to open the case and see the circuitry. Accepting that most of reality is hidden forces a profound humility. It means the questions that feel most urgent to our daily lives are occurring on a stage that is almost inconsequentially small. It suggests that the meaning we seek may not be written in the laws of our particular bubble universe, but in the fact that we, limited as we are, can nonetheless reach out with mathematics and imagination and touch the edges of the infinite. Our significance is not as the center of the cosmos, but as its curious, awakening fragment. We are the universe beginning to understand its own hidden architecture, one trembling, uncertain theory at a time. But this philosophical humility collides directly with a bedrock principle of modern science itself. The very act of reaching for the unknowable must be tempered by a rigorous question: how do we know if an idea is science at all? This brings us to a crucial, grounding theory: the limits of science and the nature of the unknowable. For all our grand mathematics and elegant models, we must confront a sobering possibility. Some aspects of these hidden dimensions, the specific Yao shape of our universe or the existence of other bubbles in an eternally inflating multiverse, might be fundamentally, permanently beyond our reach. They could reside in a realm that is mathematically beautiful but empirically silent, a domain of metaphysics rather than physics. The line between these two is policed by a powerful idea from philosopher Karl Popper: falsifiability. For a theory to be considered scientific, Popper argued, it must make predictions that could, in principle, be proven false by observation or experiment. A theory that is compatible with every possible outcome explains nothing because it cannot be tested. This criterion is the engine of scientific progress. Einstein's theory of general relativity was a breathtaking leap, but it was scientific because it made a bold, falsifiable prediction that light from distant stars would be bent by the sun's gravity. When Arthur Eddington's expedition confirmed this during a solar eclipse in 1919, the theory was powerfully validated. It had risked being wrong. This is where the debate about our most ambitious theories, like string theory and the cosmic multiverse, grows fierce and essential. String theory, in its current form, proposes a universe of 10 or 11 dimensions, with 6 curled up into a specific, complex shape. The mathematics is profound and internally consistent, but critics point out a glaring issue: we have no conceivable experiment with any technology we can envision to directly probe the Planck scale and detect those strings or measure the hidden geometry. The energy required is more than a quadrillion times greater than what our largest particle collider can produce. Similarly, the idea of an infinite multiverse of bubble universes, each with different laws, presents a profound challenge. If these other universes are forever causally disconnected from our own, existing beyond our cosmic horizon, how could we ever gather evidence for or against them? If a theory describes realities we can never interact with, can it truly be called science, or is it a form of mathematical philosophy? Proponents argue these theories are not untestable in principle, only in practice with our current tools. They point to indirect signatures like the specific patterns of gravitational waves from the early universe, or subtle deviations in the behavior of gravity at microscopic scales, which could support or rule out certain versions of these ideas. The search for these fingerprints is the phenomenology we discussed, and it is active, serious science, but the criticism forces a necessary intellectual humility. It asks us to be honest about what is a testable prediction and what is a compelling but potentially untestable narrative. This is not a dismissal of these grand ideas. It is an essential part of the scientific process, a constant check against our own imagination. The universe does not owe us comprehensibility. Some of its deepest layers may be structured in such a way that they leave no trace in our particular bubble of reality. The true geometry of the hidden dimensions could be like a locked room in a mansion we inhabit, a room whose key was lost at the moment of the Big Bang. We can deduce the room must exist from the architecture of the rest of the house. We can describe what might be inside with beautiful equations, but we may never open the door. This acknowledgement is not a defeat, it is a form of maturity. It means accepting that the human drive to know everything may eventually meet a boundary set by the nature of reality itself. Our tools, our minds, and our very existence are products of this specific universe with its specific laws. There may be truths that lie outside the light cone of our perception, forever in shadow. Embracing this limit does not mean we stop searching. It means we search with clear eyes, valuing the journey of inquiry as much as the destination of final answers. It encourages a humble awe, a recognition that the ultimate mysteries of existence might be woven into the fabric of the cosmos in a way that forever invites our wonder, but may forever elude our grasp. The future of dimensional exploration is not a matter of waiting for answers, but of building the tools to ask deeper questions. Our journey through these 30 theories has not been a map to a final destination, but a blueprint for the next generation of cosmic architects. The hunt for hidden dimensions is accelerating, moving from pure thought into the realm of tangible, audacious experiment. Imagine machines of unprecedented scale and sensitivity, designed not just to observe the universe, but to interrogate its most fundamental layers. The next great particle collider, a successor to the Large Hadron Collider, would be a monster of engineering, a ring potentially 100 kilometers in circumference or more. Its purpose would be to push matter to energies that brush against the Planck scale, the domain where the quantum foam of spacetime itself is predicted to boil. In the debris of these collisions, physicists will search for the ultimate prize, not just missing energy, but the direct production of microscopic black holes or the faint, telltale signatures of strings themselves, vibrations in the detector that whisper of higher dimensional resonance. Simultaneously, our ears on the cosmos will grow exponentially more sensitive. The Laser Interferometer Space Antenna, or LISA, is not a telescope for light but for space-time. This trio of spacecraft, flying in a perfect triangular formation millions of kilometers apart, will detect the low-frequency gravitational waves that current ground-based observatories cannot hear. It will listen for the primordial hum of cosmic strings vibrating through compactified dimensions, the echo of brane collisions from the dawn of time, and the unique chirp of higher dimensional objects merging in the dark. These are not just new instruments, they are new senses for our species, allowing us to perceive the universe in the language of geometry and vibration. Alongside these colossal projects, the quiet revolution in quantum computing promises a different kind of exploration. The mathematics of Calabi-Yau manifolds and the quantum behavior of 11-dimensional spacetime are so complex they choke even our most powerful supercomputers. But a mature quantum computer, leveraging the bizarre rules of superposition and entanglement, could simulate these environments in ways we can only dream of today. We could, in effect, grow universes in a quantum processor, testing how different shapes for the hidden dimensions give rise to different laws of physics, and seeing if any of those digital cosmos match our own. This is not mere simulation, it is experimental mathematics, a way to explore the landscape of possibilities from the inside out. Each of these frontiers, from the colossal to the computational, shares a single, thrilling purpose: to force the hidden architecture of reality to reveal itself. We are no longer just staring at the shadows on the cave wall, we are building ladders to reach the fire. The search for hidden dimensions is, in its purest form, humanity's greatest intellectual adventure. It is the story of a curious species, armed with nothing but mathematics and courage, daring to ask what lies beyond the limits of its own perception. Every null result, every refined constraint, and every potential anomaly brings us closer to a truth that may be more magnificent and strange than any fiction. Whether we discover that we live on a brane inside a hologram or as a pattern in a mathematical structure, the outcome will irrevocably redefine what it means to exist. This is the grand quest that lies ahead, a testament to our unyielding desire to understand the cosmos not just as it appears, but as it truly is. This voyage across 30 cosmic visions has taken us from the tiny, vibrating strings at the heart of matter to the immense, colliding membranes that could birth entire universes. We have stood at the edge of holographic projections, peered into branching multiverses, and considered the possibility that our reality is a simulation running on some unfathomable computer. Each theory, in its own way, paints a portrait of a cosmos that is profoundly, beautifully hidden from our everyday senses. The solid world you touch, the vast space you see, these are not the full story. They are merely the interface, the three-dimensional dashboard for beings like us, evolved to navigate a single, narrow slice of an existence with far more rooms, dimensions, and possibilities than we were built to perceive. The unifying thread through all these ideas is not a specific answer, but a breathtaking implication. Reality is almost certainly stranger, more layered, and more magnificent than our direct experience will ever allow us to know. Yet here we are, a species born of stardust and curiosity, using the language of mathematics and the power of imagination to map the shadows on our cave wall, daring to guess at the shape of the objects casting them. This relentless drive to look beyond the visible, to question the nature of our own perception, is humanity's most noble and defining trait. It transforms us from passive inhabitants of a mysterious world into active participants in a grand cosmic detective story. So tell us, which of these 30 hidden dimensions of existence resonated most deeply with you? Was it the elegant geometry of Calabi-Yau manifolds, the haunting possibility of a holographic universe, or the cyclic drama of colliding branes? Share your favorite theory in the comments below, and if you want to keep exploring the universe's greatest mysteries with us, be sure to subscribe. The journey to understand reality has no final destination, only deeper, more wonderful questions. Keep looking up and keep looking beyond.